Alright, in this lecture, we'll continue to talk about fast Fourier transform, and in particularly, we would like to discuss about the theoretical development of the fast Fourier transform. And specifically, in this case, we want to talk about the example where the number of data point capital N is equal to 4, which is the same thing like, say, 2 raised to the power 2. Alright, let us try to consider the theoretical development of the fast Fourier transform. If you remember, in the previous lecture, we already talked to you how to do the fast Fourier transform using the so-called unrigorous or non-theoretical development. But this case, we want to do in a more formal way. Okay, the so-called informal development of the fast Fourier transform we talked to you earlier. So now, according to the previous material, we say that the unknown c theta n, that vector unknown vector c theta n, can be computed based on the known value of the vector f correspond to the index k. And remember, the vector f of k corresponding to the value of the periodic function f at some specific discretized time k. And c theta n can be computed based on the known value f of k and also multiply that with w raised to the power small n times small k. And at that time, we also define for you the definition of w is e raised to the power minus small I times 2 pi divided by capital N, as shown in equation 1. So, with the definition of w as shown in equation 1, we can compute the unknown c theta n vector based on equation 11.65. Now, let us consider the very specific case capital N is equal to 4. So if it expressed in terms of 2 raised to the power r, it implies that r must be equal to 2. Now, because r is equal to 2, what it means is that we can express the index k using 2-bit binary form. Okay, now according to what we told you earlier, the index k supposed to be able to go from 0, 1 all the way up to capital N minus 1. And because capital N equal to 4 sample data point in this example, capital N equal to 4, and that's why the index k could go from 0, 1, 2 all the way up to 3. So this is the value of k expressed in terms of the base 10, the one that normally we are talking about. However, the same value of k, which could be 0, 1, 2, 3, can be expressed by using 2-bit binary form, like expressed like k1, k0. And because we're talking about the binary number, it means the value of k1 or the value of k0, it can be either 0 or 1 only. So if you express the value of k in the 2-bit binary form, then I can say 0 can be expressed as 0, 0. Similarly, I can say the value of 1 can be expressed as 0, 1. And similarly, I can say the value of 3, for example, can be expressed as 1, 1. Well, in case you forgot, let me remind you one more time again why This number 3 in here corresponding to can be expressed as 1 comma 1. The reason is because this number 1 in here, you have to multiply that with 2 raised to the power 0, and then this number 1 in here, you have to multiply that with 2 raised to the power 1, and when you add those two numbers together, that will be equal to 3. Okay? For the same reason, why this number 1 in here, why does it can be expressed like 0 comma 1? The reason is because this number here means 0 times 2 raised to the power, this number here means 0 times 2 to the power 1, and this number here 1 means 1 times 2 to the power 0, and when you add up these two numbers together, what you get will be equal to 1, because this value here is equal to 1, and the reason because 2 raised to the power 0 is equal to 1. So that's all. What I'm trying to tell you is any index k can be expressed using 2-bit binary number as k1 comma k0. So that way, instead of saying the value of k go from 0, 1, 2, 3, now I can say the value of k can be going from 0, 0 to 0, 1, 1, 0, and 1, 1. Okay. In the next slide, I can make even a more compact formula for you by saying the index k could be expressed as 2k1 plus 1k0. Now, actually, for future development, I prefer to write this one in a slightly different form. Instead of say 2 times k1, I prefer to write like 2 raised to the power 1 times k1. Plus, instead of saying k0, I prefer to say like 2 raised to the power 0 times k0. Obviously, we all agree that this expression is the same thing as the right-hand side of equation 3. However, if you express like in the form that I just told you, 2 raised to the power 1 times k1 plus 2 power 0 k0, if you do that way, we can generalize our result into much easier, more general situation. For the same reason, we can also express any value of the index n as 2n1 plus n0 as shown in equation 4. Again, that equation I prefer to express as 2 to the power 1 times n1 plus 2 to the power 0 times n0. If you express like that form, then you will see in the future we can generalize our result, the result of this chapter, into a more general situation. Now, according to the previous slides, because k1, k2, n1, the n0, they're all binary number. That means the value of k1 or k0, n1 or n0, they can be only either 0 or 1. So now with those new notation introduced, then we say equation 11.65 that I showed you on the previous slide now become equation 5. Now let's take a look why that is the case. Let's take a look at equation 11.65. You see, if you look on equation 11.65 on the previous slide, the only thing we did is whenever we see the index n, we replace it by the new formula for n. Whenever you see the index k, we replace it by the new formula for k, and we do again for the new formula for k and the new formula for n. So we look at that equation and we just replace the value of n and k by the new formula for n and k. So by doing that, as you can see, this is what we get. You see, instead of n, now we say n1 comma n0. Instead of k, we say k1 comma k0, right? As you can see here, the c theta depending on the value n, but that value n now become a pair of number n1 n0, and the k now become k1 k0. And then also, if you notice, in the previous equation, which is equation 11.65, here we have is n. It used to be called n. Now we call it 2n1 plus n0, as you can see from equation 4. Similarly, in equation 11.65 on the previous slide, we used to have this term, we used to call it small k. But now, instead of small k, we call it 2k1 plus k0, as you can see from equation 3. So, all I did is equation 11.65, I put that in the new notation, and that become equation 5. Now, the next step that I